In this lecture, we are going to see the quantum wave packet and their evolution, also their property. This is the typical wave packet, which is a superposition of so many sinusoidal wave of different amplitude and different frequency. If you add it, you will get here the x-axis is wave function. Modular square of the wave function is, is amplitude. You have maximum amplitude here, and x-axis is position. Now this wave packet will move with respect to time, like this. So we are going to deal with the wave packet in this lecture. Now we will see the significance of wave packets. First and foremost is the physical representation of particles. A plane wave extends infinitely in space, which is not physically realizable. That means that particle can be anywhere in this space from minus infinite to plus infinite. But the wave packet is a localized superposition of waves, just I have explained, representing a particle confinement to a finite region of space. So that is a first important point about the wave packet. Next, wave packet illustrates the Heisenberg uncertainty principle. We will see it in due course. The narrow wave packet uh, gives accurate position but broader spread in momentum. This trade-off is fundamental to quantum behavior. So we are going to see it in detail in this lecture. Third point is time evolution. The wave packets spread over time due to dispersion. This also we are going to see now. And this spreading explain why quantum particles do not remain perfectly localized. Then another important point is this bridges between quantum mechanics and classical physics. That is, the center of the wave packet often follows the classical trajectory via Ehrenfest theorem. This makes the wave packet crucial for understanding the quantum to classical transition, which we are going to see now. Now we will see the motion of wave packet. The wave packet is a superposition of plane waves of different frequency and wave vector and amplitude. If it is a single frequencies, that is a single sinusoidal wave, as I said, the particle may be here from minus infinite, anywhere between minus infinite to plus infinite. You cannot precisely measure the position. But what about momentum? This is fixed energy because it's a fixed frequency. You will have p squared over 2m. Energy is equal to p squared over 2m. So since 2m is a constant, E is proportional to p squared. So naturally, since E is a constant, P also a constant. Then how to make it localized wave? In the next slide, we are going to see it visually. You add so many number of so many number of sinusoidal wave with different frequency and different amplitude, then you will get a narrow wave packet. So the time-dependent wave function can be written as using Fourier technique, summation over n, Cn psi n of x e power minus I ent over h cross. I have separated the position dependent wave function. This is time dependent wave function. This Cn is probability amplitude. So Cn by definition is the inner product of psi n nth state vector. That is wave function of nth state to the total wave function. So it's the inner product of nth state wave function to total wave function. So that is how much component projected in psi n over psi over psi n. So that is as the probability amplitude or expansion coefficient. We have seen that single fixed frequency, the momentum is fixed because energy is the same, h nu. So E is equal to, just now I explained P square over 2m. So E is fixed means P also fixed. You can measure the momentum accurately. But what about position of a single frequency sinusoidal wave? It is infinite, from minus infinite to plus infinite. You cannot locate particle exactly, but you can measure the momentum exactly. Now we are going to add three sinusoidal wave of different frequency and the sum. So what will happen now? Here you can see we are adding three different sine waves. One is red color, which has a different phase and a different frequency, and the other one is blue color, which is having different frequency and a different uh, phase vector, and also the green color one, different frequency and uh, different phase vector. So if you add all the three, you will get some as shown in the black color wave. So here you can find one maximum and here one maximum. The x-axis is amplitude. The square of the amplitude is a probability of finding the particle. So here you can find the particle, here you can find the particle. But sine wave you can find, for example, you take a red color wave function, red color sine wave. So you can find particle here, here. It will go up to infinite. So this is called wave packet. That is addition of sinusoidal wave is a wave packet. We know the time-dependent wave function psi of x and t can be written as e power plus I kx minus omega t. Now, to create this wave packet, we are going to add the sinusoidal wave of different frequency and different phase vector. So, different wave vector. E power it is equal to the cos theta plus I sin theta. This is basically the linear combination of sinusoidal wave. So, you know it. Then you add delta k, that is a small deviation from the wave vector, and delta omega, that is a small change in the frequency. Similarly, the minus, this is minus. So you are adding the wave function, time dependent wave function with positive variation in the wave vector and frequency. So here you are using negative minus delta k minus delta omega. Now in both term contain e power I kx minus omega t as a common. You can see I will use different color. You can see this is kx and omega t. Here also kx minus omega t. So I can take it out. E power I kx minus omega t. The remaining thing is in the first term you have e power I plus delta kx minus delta omega t. And here in the second term you have e power minus, because here both the terms are negative. So minus I delta kx minus delta omega t. So what is sine I theta plus sine minus I theta is 2 cos I theta. Sorry, 2 cos theta. So which is equal to 2 cos this delta k x minus delta omega t. So this is actually the envelope modulation parameter. This will modulate your time dependent wave function. This wave function is modulated by this cosine term. So if you add sine wave of sinusoidal wave, maybe cosine wave, sinusoidal wave of different frequency, it will become a wave packet. Here you have two wave packets, this one and this one, this envelope, Gaussian envelope. This is actually the movement of wave packet. With respect to time, this wave packet will get moved, which we are going to see in the next slide. Now we are going to see the propagation of Gaussian wave packet. Here we have, I have shown in blue color, some of different sinusoidal wave of different frequency and different phase factor. Then the combined one result, I am going to draw the envelope using this black dotted line. So this is the Gaussian envelope. Now this start uh, propagating and the wave function will get propagated like this. So this will move like this with depends on the time, it will move like this. Then we will see it further. Now we are going to see the phase velocity and group velocity. First we will see the phase velocity. That is, we have just now seen that psi of x and t is equal to e power I kx minus omega t multiplied by this modulation factor 2 cos delta x delta kx minus delta omega t. So now this is the phase factor kx minus omega t is a phase factor. Then what will happen if you differentiate this with respect to time? You will get this k tx over tt minus if you differentiate this with respect to time, you will get minus omega, which is equal to 0. This phase vector is a constant till it is always constant. Here I like to say some interesting phenomena. Since phase factor is constant, what will happen if t increases? If it is negative sign, that also important. If t increases, this will become second term will be increasing one. So naturally, first term has to increase. So here k is a constant, so x will increase. That means it will move towards the right side. If it is plus, what will happen? Kx plus omega t also a constant. If t increases, x has to decrease. So this will move in the opposite direction. Remember that if it is plus, it will move in the opposite direction. That is negative x-axis. If it is minus, it will move towards the positive x-axis. That is a very interesting thing. Now we will come back to it. Since it's a constant, if you differentiate this constant, t psi by dt equal to 0. So this k tx over dt minus omega is equal to 0. Then what is tx over tt? You bring this omega to the other side and k also to the other side, which will become omega over k. Now you multiply and divide by h cross. So the numerator is h cross omega. That is mv squared over 2. So half mv squared, first term, h cross omega. H cross k is momentum, mass into velocity. Here, this m will cancel with this m, and this v will cancel with this v squared, which will become v. So the base velocity is equal to half of v, that is half of the particle velocity. That is very interesting thing. It is not equal to the original velocity of classical particle. Now we will see the group velocity. Already we have seen the time dependent wave function. As usual, this is the envelope. Envelope is this particle moves with a different velocity, different pace, and this envelope is a Gaussian one. This envelope is modulated by this. So pi envelope is equal to delta k x minus delta omega t. So as usual, you take a time derivative of this. Then you will get delta k tx over tt minus delta omega. Because it's a constant, it is equal to 0. That means delta k t over tx, this one, minus delta omega is equal to 0. Then you can rewrite this tx over tt is equal to, you bring this delta omega to the other side and delta k to the other side. So this will come into the denominator. So the group velocity by definition is equal to t omega over tk at k naught. That is wave vector at k naught. Then Vg is equal to t omega tk, which is equal to t over tk. Omega, we know omega is equal to h cross k squared over 2m. So if you differentiate this with respect to k, you will get 2 h cross k over 2m. Now you can change, cancel 2, and h cross k is the momentum mv, and the denominator you have m. So this will cancel out. You will get v. Simply this v is the classical velocity. So group velocity is obeying the classical particle. It follows the classical trajectory. So quantum particle will behave like a classical one. This connects to quantum mechanics and classical mechanics. If you find this lecture helpful one, kindly subscribe. Also share my video and join my channel for the growth of my channel. Thank you very much for watching my video continuously and supporting me. Thank you very much.